Hey everyone, so this is going to be a Chapter 6 review of the Chapter 6 review worksheet. Okay, so make sure you've taken out this worksheet if you want to review this. So F net equals ma, so Newton's second law equation there. So this is out of section 6.1. So again, if you don't know where to find this information, always look at the notes that I give you, but also look at your book. Okay, so I labeled it with the sections that you can find these answers in. All right, I even made them a bigger font so that you'd be able to see it, but it's okay if you didn't. All right, so let's move on. So section 6.1, number 1, what produces acceleration? All right, so just looking at Newton's second law equation there, F net equals ma, so we would say that the net force produces your acceleration, or an unbalanced force, or a non-zero net force acting on an object is going to produce acceleration on that object. Okay, so as we previously learned, in order to change a motion of an object, you need to apply a force. Okay, so that motion actually changes. It changes the acceleration of your object. So in chapter 4, we defined acceleration as a time rate of change of velocity. What other equation for acceleration is given in this chapter? So in this chapter, we were given that acceleration is equal to your net force divided by your mass. So I don't know if you remember from chapter 4 when we were talking about linear motion, but acceleration is also equal to the rate of change in your velocity. So the way your velocity changes over time. So Vf minus Vi all over t. But you can also solve for acceleration using Newton's second law. A equals your net force over m. So in section 6.2, is acceleration directly proportional to mass, or is it inversely proportional to mass? So acceleration and mass do hold a proportionality. It is an inversely proportional relationship. So as you increase your mass, you expect your acceleration to decrease. As you decrease your mass, you expect your acceleration to increase. So as you can get a kind of a good idea there is, as you increase one, the other one decreases, or as you decrease one, the other one increases. So number 4, if two quantities are inversely proportional to each other, does that mean one increases while the other increases as well? No. Inversely proportional means that, as one increases, the other one decreases. As one decreases, the other one increases. What number 4 does show is a directly proportional relationship, where the one increases and the other increases, or one decreases and the other decreases. So what holds direct proportionality in this chapter is your net force and your acceleration. So as your net force increases, your acceleration increases, and as your net force decreases, the acceleration decreases, which again shows a directly proportional relationship. So section 6.3, if the net force acting on a sliding block is tripled, what happens to the acceleration? So you might right off the bat recognize that the acceleration is going to triple, but if you forget, you can always draw a picture. Okay, so let's just say that our block is 1 kilogram, and originally we were producing a force on it of 1 Newton. Okay, so now we want to see what would happen if we increased our force. So we now put 3 newtons of force on that block. So what do we expect to happen with our acceleration? Well, using Newton's second law, acceleration is equal to your F net divided by the mass. So acceleration is equal to 1 Newton divided by 1 kilogram, which is equal to 1 meter per second squared. So that was our original acceleration of this block. But if we tripled our net force, we would get that the acceleration is equal to 3 newtons divided by the same amount of mass. The mass never changes, and this would be 3 meters per second squared. So as you can see, as you triple your force, your acceleration triples. So number 6, if the mass of the sliding block is tripled at the same time the net force on it is tripled, how does the resulting acceleration compare with the original acceleration? And this question might be seem like it's really hard, but go ahead and draw a picture of what it's asking you to look at. So if we have a 1 kilogram block again, and again we're going to apply a force of 1 Newton to it. So if we were to use Newton's second law, A equals your net force divided by the mass, we would get an acceleration of 1 meter per second squared. So if we were to triple the force and also triple the mass, what do we expect the acceleration to look like? So let's do so. Let's triple this force and let's triple this mass. And let's solve it out. So A is equal to F net divided by the mass. So A is equal to 3 newtons divided by 3 kilograms. Oh, we should see that the acceleration is the exact same. Crazy. But not really, right? Because if we're increasing that net force and we're also increasing that mass, the acceleration is going to be the same. So section 6.4, number 7, a box moves across the floor at a constant velocity. If a 60 Newton force is a 60 Newton force is being applied to the box, what is the force of friction? So again, let's draw a picture. So we have this box. We're not sure what mass it is, but it's not really needed for this problem. So we have a force applied of 60 newtons. And we were told that this block is going at a constant velocity. So a constant velocity means that the acceleration is equal to 0. Because if it's a constant velocity, there's no change in our velocity. So constant velocity, our acceleration is equal to 0 meters per second squared. So if our acceleration is equal to 0 meters per second squared, what does the sum of the forces have to be? Well, again, if we were to use Newton's second law, F net divided by the mass. Again, we're not really sure of the mass, but that's okay because we know our acceleration. Our acceleration is equal to 0. So what does this have to be equal to? Well, F net also has to be equal to 0. Okay? So in order for the sum of the forces to be equal to 0 here, what does this force of friction have to be equal to? Well, it has to be equal to the supplied force. So the force of friction should be negative 60 newtons or 60 newtons in the opposite direction. Because as we know, the frictional forces always act opposite to our motion. So number 8, suppose you exert a horizontal push on a crate that rests on a level floor and it doesn't move. How much friction acts compared with your push? So there must be more friction acting on the object than what is being applied, which is why it's not moving. So how great is the air? So number 9, how great is the air resistance that acts on a 10 Newton sack that falls in air at a constant velocity? So if we were to draw a picture, let's just use a ball. And the ball's mass is equal to 10 kilograms. And we know that the ball is being acted upon by its weight, so it's being affected by gravity. So Fw equals mg. So we also know that this is in the presence of air resistance. So air resistance is also going to have an effect on this ball, so I'm going to label it as Fr. So right now we're not really sure what this air resistance is equal to, so let's look back at the problem. So how great is the air resistance that acts on a 10 Newton sack that falls in the air at a constant velocity? Again, constant velocity here is the key word. Because constant velocity tells us that the acceleration is equal to 0. And again, if we know that the acceleration is equal to 0, and we plug it into Newton's second law, then if we multiplied it by our mass, it would mean that the F net, or the net force, is also equal to 0. So in order to have a net force equal to 0, what does this force of resistance have to be equal to? Well, it has to be equal to the weight acting down. So if we were to solve for the weight, which is 100 newtons, then this force of air resistance would have to be 100 newtons. And I just realized that I misread this problem. I read this as a 10 kilogram mass instead of a 10 Newton force. So the force of air resistance would still have to equal the force that is acting on the object itself. So air resistance would actually be 10 newtons there. Sorry about that. Okay, so section 6.7. So does air resistance on a falling object increase or decrease with increasing speed? So as we learned about the other day, air resistance depends on your two things. It depends on your surface area, and it also depends on your speed. So as you increase your speed, you're actually increasing your air resistance. So 17, if two objects of the same size fall through air at different speeds, which encounters the greater air resistance? So again, it's the one that is moving faster that is going to be encountered with the greater air resistance. So what is the acceleration of a falling object that has reached its terminal velocity? As we said multiple times, terminal velocity is when your weight acting down is balanced by the air resistance acting back up, so your acceleration is equal to 0. So what, besides speed, affects the air resistance on a skydiver? So again, air resistance is affected by your surface area, or your area, and your speed. Okay, so what besides speed? Your area. How much air resistance acts on a falling 100 Newton box of nails when it reaches terminal velocity? So we are given that the box of nails is 100 newtons, so that is its weight. So for something to reach terminal velocity, the sum of the forces has to be equal to 0, so air resistance must also be 100 newtons acting back up on the object. So F equals ma practice. So number 21, boxes of various masses are on a friction-free level table. Okay, so how are the net forces of each, so what are the net forces of each box, and what is the acceleration of each box? So so for A to solve for the net force, you have 10 newtons right, 5 newtons left, so the net force is equal to 5 newtons to the right. For B, you have 10 newtons left, 15 newtons right, so the net force there is 5 newtons right. For C, you have 10 newtons left, 15 newtons right, so the net force there is 5 newtons right. And for D, you have 5 newtons left, 15 newtons right, so you have a net force of 10 newtons to the right. What is the acceleration of each box? Well, your acceleration is equal to your net force divided by your mass. So the acceleration should be equal to, for A, 5 newtons divided by 5 kilograms, so it should be 1 meter per second squared. For B, it should be 5 newtons divided by 10 kilograms, it should be 0.5 meters per second squared. And for C, you have 5 newtons right, 5 kilograms, and so it should be 1 meter per second squared to the right. So D, you have 10 newtons as your net force, and you're dividing it by your 20 kilograms. So again, it should be 1/2, so 0.5 meters per second squared. So number 22, calculate the acceleration of a 40 kilogram crate of softball gear when pulled sideways with a net force of 200 newtons. So we need to calculate the acceleration. So A is equal to F over M. So we have a net force of 200 newtons, and we need to divide it by that 40 kilograms. So we should get an acceleration of 5 meters per second squared. All right, I hope this was helpful. If you still have questions, please let me know. I'll see you all soon.